Hello and welcome to another episode of Inside XRF. My name is Konstantin Brentgens, and we can see the topic of today's episode in front of us already, I hope. So we'll talk about creating a analytical method for a wavelength dispersive X-ray spectrometer today, and we're going to go through the different steps that we need to take to establish such a method. As always, feel free to write questions in the comments. We'll see if we can address them at the end. And if time runs out, we'll just get back to you by email. So if you're registered to the course, just send the email. That's anonymous. If you are using like a guest account on another computer, you can always also write the questions to simply info@fluxana.de, and it'll end up with me, and I'll probably find the time to have a look at it. Okay, so let's jump right into it. Let's see. Okay, so repeated visitors might be familiar with the formula we are usually using. Today's topic focuses solely and entirely on the analysis part in the X-ray machine. So we're not going to talk about the other topics that result in good analytical results. We'll just focus on the X-ray side today, and our main goal is what main questions are, what steps do we need to take to create a analytical method, and what other parameters we need to decide on when developing one. And then the second part will talk about calibrations, meaning how do we get the signal into a concentration result, for example, and what possible corrections can we apply there if they are necessary for our analytical accuracy. So when it comes to the creation of an X-ray method, we always have to think about the measurement parameters, and that basically includes the setting of our tube, the collimator, the crystal, and the measurement positions on a wavelength dispersive unit, and also the detector optimization in terms of the PhD. You may have read that in one of your softwares, or it's sometimes also called PHA for pulse height distribution or adjustment. So it's basically the controlling of the electrical part. So to summarize it, for each element that we want to analyze, so for each analyte, we need to find a tube setting for the excitation. We then have to decide the goniometer settings, the whole part on the right of our sample. This is our sample here. The part on the right, the whole assembly is usually called goniometer. And for each of the elements or analytes, we have to decide on the collimator, the crystal, and, analytical angle, obviously, and then the detector. So this is something we need to set up for each element in order to have a good performing analytical method. And the software that you are using, each one of them usually comes with a preset, let's say. So when we go through each of these to each of these parameters, we'll go one by one now. So we'll start with the tube setting, and you can see here there is an overview about the elements measured, and then these are typical tube settings that are used as a sort of standard library. To understand tube settings, it's usually two parameters. It's the kilovoltage and the milliampere. And as a rule of thumb, to kind of summarize it, we need the high voltage, the high kVs, to excite the heavier elements. So the elements with the higher atomic number in the periodic table, they need more kV. So going from left to right and top to bottom here, we just need more kV. And higher tube currents, the MAs, increase the intensity in total. So if you would divide your KV by half, but multiply your MA by factor 2, you basically double your intensity. And this is particularly useful for the lighter elements. So if we're looking at our overview here, you can see that the yellow ones, beryllium to chlorine, they go like low KV, high MA, and then it kind of switches. One thing that FLUXANA likes to do for a lot of our application on most of our X-ray spectrometers is to work on a constant power. The power being the product of both. KV multiplied by MA is basically kilowatts. It's the power of the tube setting, and we like to keep that stable along one analytical method because that is less stress for the X-ray, for the tube and the generator. So it increases the lifetime, the lifespan of your equipment. And usually you can find a good middle ground where you have enough KV to excite the heavier elements and enough AMA to excite the low elements as well. So you kind of find a compromise. There are some applications where you have to maybe split it into different groups. If that's the case, make it in a smart way as is done here. The product of the KVMA is always the same. It's always 2.5 kilowatts. So you can vary the MA and KV, but you want to keep the product as a constant to save your equipment from unnecessary stress, let's say. Collimator being the first part in your machine behind the sample. This is kind of, I always like to compare it to an open window or an open door. The more you open it, the more intensity you let through, but at the same time, the more interference you let through. So if we're looking at our nice little picture here, we have two lines here. They are maybe a bit hard to read, but this is vanadium K alpha and barium L beta, vanadium being the left one, barium the one on the right. And now we took one sample and we measured it with different collimators in one of our machines. As you can see, these are labeled by a degree change, and basically the highest number is the coarse one, and then the lowest number is the fine collimator. So if we leave the thing entire open, you have the line for the 2.6 here, and in this case, we can't even tell the difference between the two elemental lines. The energies kind of they kind of pile up into one big peak, and we can't tell the difference. So that one would actually not be usable. But the next ones are, you can see the 0.6, which is the next finer one. We can actually see two peaks, and then the same for the 0.25 and the 1.5. And we have to make a decision which one to use based on that. So larger or finer collimator, the other way around. Finer or smaller collimators means less intensity, but a better resolution between the peaks. So again, in this case, we decided on the fine one, on the red one, but in this case, in this example, I would also say the blue or green one would be usable if we use some sort of background construction to kind of get a better solution between the two. We always have to keep in mind this is only one sample. So now when we have multiple samples where the concentration changes, the peaks change in height and position. And we have to think about that when we're looking at our goal at the end to have a performing analytical method. Okay, next parameter, the crystal. The crystal is the unique piece in a wavelength dispersive unit that kind of splits the inter-element spectra we get, the multi-element spectra we get from our sample into different wavelengths, and the detector position then can be set to the one thing that we actually target. So quite similar to a prism, we basically split multiple wavelengths into an area, and then we can just focus on a specific wavelength, which is corresponding to the energy of a specific element. We do have a table here about the available crystals in one of our machines. By available, I mean these are all the ones you can buy. These are not all the ones we have installed in our machine. For example, we don't have the 420 LIF and I think we are also missing the ADP. But a good selection of those, usually what you have is an AX, a PET, and one LIF. And there are a few extra crystals here that have certain advantages for certain elements. For example, the germanium one here, which is really good for phosphor to chlorine, gives you a higher resolution and high sensitivity. So this is usually what we use for phosphor, sulfur, and chlorine. Again, not all machines might have them, but there is a list here, and the names might change, but the crystals are all the same. These are the parts in the machine being responsible for splitting your multi-element spectrum into single element energy, so to say, where we put our detector and then just capture that particular energy. So what's the effect of the crystal? We have an example here. Again, we have the same lines before. We have the vanadium K alpha and the barium line that were mentioned. And in this case, we took one sample and we measured it with the LIF 200 and then the LIF 220. And as you can see, first of all, different elements can be measured with multiple crystals. We could also do that with the PET, for example. So there is a certain overlap for crystals, and usually the setup of your machine will kind of depend on what you want to analyze later and then give you like an optimum. You don't need all crystals if you're only measuring one material all the time. But yeah, in this case, just a comparison for the 200 to the 20. First of all, we can detect both of these lines very well here, but we can notice some changes in the shapes and positions. So if you're looking at just the position of the peak, it kind of works. It goes a bit apart when you're looking at the 220 here. Just like the barium moves out to the right a bit. And at the same time, if you're looking at the intensity level, it changes slightly. So basically, the LIF 220 has a better resolution, just making it a bit wider, making it more separate, but it has less sensitivity, so the peaks drop down a bit. And you can use this to your advantage if you have both of them available to just select the one that gives you the best signal in the end. And in our example case here, the two lines, we opted to use the 200 just to get like the optimum in intensity. And yeah, then I think we will probably made a background correction here to the left and right so that we kind of get rid of the noise in the background, so to say. Speaking of backgrounds, this is an optional thing if you're using a wavelength dispersive unit with a goniometer. There are also machines with monochromator channels, so you basically have multiple channels situated around your sample. They don't have the option for a background. It's just not available. It's all fixed. But when you're using the gonio, you can opt for a background or even more. And it's just a matter if it makes sense analytically. It's basically, do you want fast analytics or more precise analytics? And then you also want to maybe pay attention to your sample preparation and the level of intensity. And one thing to keep in mind is when you're using background corrections, you should make sure that your background positions are free of line overlaps. It's not a good idea to put the background measurement in the peak of a different element. This will just mess up your intensity as a total and give you trouble later. So in our example here, for example, sodium and magnesium, we always like to actually have two background positions, and all the other ones we opted for only one. Detector, sort of the last parameter, also at the end of the analytical process. There is some very nice pictures here. I just want to kind of gloss over them a bit because it gets really technical here. And I think this would kind of be a bit too much for our basic course today. So usually what you have is the flow proportional counter. That's basically a Geiger counter, which uses up your argon methane that you usually have to attach to the machine. So that's what's using the PT10 or the argon methane gas. It's a gas-filled tube basically, and the X-rays, they basically make a little short circuit and create a signal which is counted. And then we have the scintillation counter, which works a bit differently. In this case, the the quants, they make sort of a little lightning, a little optical impulse, and that is multiplied and then counted. In the end, both of them are proportional, although both counting methods are proportional to a certain energy, which again is representative or representing a certain element. The table, the periodic table down here kind of shows this, being the green elements are usually measured with the FP, and then the red ones are usually done with the SC. But again, there is an overlap, there is a gray zone, and depending on your manufacturer, actually, some start at a lower energy, switching from the FPC to the SC, for example. Both work and both perform fine. It's just, sometimes you have a small advantage of using the other or not. But yeah, you usually have those two, and the line library will tell you when to use what. The optimization here, excuse me. The optimization here, what I mentioned before, this pulse height adjustment or pulse height distribution, is basically a threshold and a window, so a lower limit and an upper limit, and everything in between is summed up as your total signal. So what you want to tell or what you want to investigate is, or what we always try doing is, we're using the highest intensity of our samples and the lowest one, and we put them together and make sure that the signal peak, which is a line diagram, is captured well within our two limits. And if not, we kind of optimize. But in my experience, 99%, let's say 95% of all the line libraries out there, they're already having very good settings, because the technical standard of these machines is quite high. So that was the first topic. The setting up of our line parameters, of the measurement parameters for the elements. And once we have that established for all the analytes, we need to make the calibration also for each one. And in calibration, we have to talk about a few things listed here. So the first thing is the calibration now takes the signal, which we have up here, the spectra, the intensity of lines, combines them with concentration results that we know, for example, from a CRM. We have a paperwork that gives the documentation. And now we make a evaluation that translates the measurement signal, the intensities, into concentration. So that's what we usually call calibration, and we're making these calibration curves. Curves is a bit misleading here, because usually in XRF you can find linear calibration curves. The correspondence or the correlation between intensity, and intensity being the amount of atoms, and the concentration in your sample is linear. So that's what you always want to go for. There are exceptions, but yeah. Why does it not always work? Because we have interferences, and we here at FLUXANA like to put interferences into two categories. The first one being interferences of the spectrum or spectral interferences. And the question is, for example, if we have a situation like this, and there is a peak next to our analyte peak, now what happens if this one goes higher and this one goes lower? Will it overflow at some point and create an artificial signal, which we would call a line overlap? And this needs to be investigated, and if we find one, we need to make what is called a line overlap correction. So we are making a correction on the intensity, on the measurement signal, before we then go into the mathematics of creating a concentration value out of our results. And there are some very known examples. For example, we know that bromine L alpha is right smack on the aluminum K alpha line. So the energies are very similar, and they are hard to distinguish for the setup, no matter what your machine is. So especially in our applications where we work with a lot of fused beads, bromine is an additive that we might add to prevent sticking and wetting. It's the non-wetting agent. So we are adding it artificially to our recipe, and at the same time, we're adding aluminum signal, which equals more aluminum concentration. So you can see that down here, the black, this is one sample done without and with bromine, the black spectrum being just the normal one. which like 0.1% alumina. And then we added some bromine here just for fun. The sample works without, but for fun, we added some bromine here. And as you can see, the L-alpha peak is just way larger. So we would find way more aluminum than is actually in the sample. So we have to correct it with a line overlap correction before we then go with the corrected intensity into our calibration. Another one for we also use iodide as an additive, and we usually find that iodide gives us more titanium signals. So again, there we need to make a correction. Yeah, once this has been taken care of and we have kind of gotten all the signals into a clean range, there is also matrix influence or concentration-based influences. So this would be, the classical term is matrix correction. This is when the elements interfere each other, when they have some sort of effect on other analytes. And in order to explain that, we'll go into the way of alpha correction a bit later. So there is a little like a little sort of intercoil, how to say, like a little break here. When it comes to calibration, the easiest way you can have is just the base curve, no correction, and then let me just read this term to you in normal voice. The concentration of any analyte is A0, the intercept plus A1, the slope multiplied by the intensity of that analyte. So it's very simple. But usually not what you find in practice. Usually what you find is the theoretical curve would be like this, but the reality is something like this. It's bended. So if you're working on standard materials and you don't find the straight line, you find this curve. And this comes down to an inter-element effect here, one that is very well known. In this case, it is if you have a mixture of chrome and iron, these being very similar energies, let's say, they kind of influence each other. And what happens is that if the iron inside your sample gets excited, you either get this as an iron energy that you can measure, or on the way out, it cross-excites chromium, which means the iron signal gets absorbed and the chromium signal gets enhanced. You find more of it because of the secondary excitation inside the sample. So in order to make this workable, or in order to compensate for that in our analytics, because obviously samples are, they have various concentrations of both, and we want to find out what is the real one. We have to be a bit more complicated on the correction or on the calculation. So we are going away from our easy linear calibration to one that is corrected with what is usually called alpha correction factors. And I don't want to go too much into the details on how this is calculated. You can find the formulas in a lot of, usually in the manual of your software, it's all there. The interesting part is we use these alpha correctors. We calculate them on using our sample set where we know the concentration of both parties. We use those, we calculate the alpha factors, and they kind of bend the curve in the right position. So in this case, the chromium signal will be corrected based on the concentration of iron. And we do that for all the sample, and then we have our alpha factor that is kind of the one that is correction. So in order to do this, what is called empirical correction on alpha factors, or the establishing of empirical alpha correction factors, is you need a lot of samples, and then you need to investigate what is happening. You need to look for systematic effects. We have to be aware that the main components, which is present a lot, usually causes these effects. And most softwares allow you to play around a bit, to experiment, to just, hey, calculate this correction factor for me. And if it's negative, there is certain indicators on how to decide then if this is usual or not. But mainly what we want to achieve is, in our example here, we were playing around a bit, and we you can't really see, but it goes from 0 to 6 corrections numbers here, and you can see the SEE, the estimated error. We basically, we cut it down from 1.3 to 0.5. So we improved a lot by using and introducing these alpha corrections factors. But there is, of course, a limitation. In order to do that, we need a lot of samples. The rule of thumb is that in normal calibrations, without corrections, when we only use A0 and AY, the slope and intercept of our curve, we need at least 5 standards. I would say 3 is the absolute minimum if you don't have anything more available, but 5 is a good number with a good distribution. And that gives you a reliable course. Now, if you want to do alpha correction empirically, you need additional 2 or 3 standards for each interfering element. And that makes the standard set grow large quite quickly. So, and there is a little formula here. So if you want to go for like 3 intermediate, if you want to go for a calibration where you know you want to use 3 interfering elements, you need like a set of 11 to 15 standards. More is always better, but the question is, are those available? And let's assume these samples are not available. Then we have a third option for correction, and that is what is called the theoretical alpha approach. This one works with smaller sample sets, but all of them have to be described 100%, as well as the preparation needs to be known. You have to give the software more information about your samples and the total, like the composition of those, and they need to be described to 100%. Usually the limit is like 99.5 to 100.5. There is always some room for error, but you're not allowed to leave a major component out of this description. And you also have to describe the sample preparation that you are using, like a dilution factor for on. And there's also usually some machine components, like some, not components, but like some variables in the machine, like the angle of your tube and whatnot. But this is usually taken care of by the software. He knows that already. So you give these information into your systems, and then he can calculate those factors for you based on theory. That makes it easy, a lot easier to use with the setup. But you have to be aware you need 100%, but then you can use less standard samples. And we have an example here. On one of our software packages is simply pressing a button down here. They call it variable alpha. So you can simply switch with this one to on and off, and you can see the improvement in your STD or in your SEE immediately. Like we go from 0.5 to 0.17. So it's quite nice and easy to use, but you need to do a bit of preparation before you are able to use it. The formula gets really complicated at this point. So the basic idea is that we are using the mass absorption coefficients, which we know from the energy of our lines in the setup of our machine. Well, we can read them from a table that is in the software package. We use that to calculate the total sum of all influences for all elements. That's also why we need to describe them 100% in concentration, so that he can calculate for us. Luckily for us, modern technology, modern computers are really fast with the calculation. You don't see that anymore. It's just like you click the button and he does it. But yeah, we have to give him a lot of information, and then he can calculate that for us, and he can apply it to any calibration in order to improve the accuracy. So basically, when it comes down to the building of the calibration part, where we take our intensities and transfer them into a concentration results, we have these 3 models. This table, I don't really want to read it now because we are kind of running low on time. But yeah, we basically have the easiest one being no correction. The problem here is that there can be matrix effects that we are overlooking, and they affect the precision of our analysis. So it works good for liquids in these likes, but if you have more complex samples, it gets difficult. Empirical alpha corrections is nice for a specific material group. For example, it has been done in the cement industry as a quality control for a long time, and they knew which elements they would need and which samples they would need to describe the problem, and then they could make a nice empirical calibration that always gave the same quality. And in the recent years, theoretical and empirical have kind of, how to say, changed a bit. I think due to the ease of use and the modern computers nowadays being so fast, theoretical alpha correction has been kind of the go-to solution now. Also, it's usually cheaper because you need less standards. So this is kind of the new trendy one. What we have to keep in mind here is we have to know everything about our samples. We have to know 100% of the composition, and we have to know the sample preparation, and it needs to behave as the theory said. If there is problems in the sample preparation, this kind of breaks the method. So you have these three options to make a calibration, and then the final step, once that is done, we have created our measurement parameters in our method. We have done our calibration and corrections. We have to be aware that XRF will always be relative. It is always comparing to standards, for example. So we have to be aware that as our spectrometer ages, the validation of our calibration is difficult to prove. So you have to think about some sort of long-term stability, and this is usually done in the case of drift correction. Or drift correction monitoring samples works mostly automatic nowadays, but you have to attach it at the end of your method development. So changes in the spectrometer, for example, the wear of your X-ray tube or your detector just aging and losing a bit of sensitivity, it needs to be corrected with a drift correction or monitoring sample that is basically measured multiple times and just always changes or calculates back your signal to the day zero, the day of the calibration. So this is something at the end of the process to keep in mind. To summarize, when we want to develop or make a new wavelength dispersive method, we first have to think about the machine side, the parameters of the channels, so that we find good parameters for all the analytes and also the possible interfering elements. So tube setting, collimator, crystal, and detector. Once this has been decided on, we need to make the calibration itself and use the necessary corrections as they emerge. Less corrections needed is always better. So if your application, your method works without corrections, that's fine. But we might have need some time to investigate if there are needed corrections that we need to apply. And then finally, we need to think about long-term stability. So we need a suitable drift correction monitor program that usually just includes a few solid sample like drift correction samples that you attach to it. And then most of the time you can use a few monitors to run multiple applications or to correct multiple applications in the background. Yeah, that's it. I'm only 3 minutes past my time, so there are a few questions, I think, but I'll get back to them by email then. I thank you very much for your attention. And hopefully see you on the next webinar. Have a good day and bye-bye.